Success. All right. So, welcome back after your few snow days, if you had snow days. Hello, First Hand Friday folks over here in the corner. Hello. Over there inside. Excellent. Hello, hello. Welcome to second semester general chemistry. For those of you who are normally in this class, my announcements are, we were supposed to have a quiz on Wednesday. Obviously, we weren't here on Wednesday, so I moved it to Monday. So it'll still be the same material that we covered on Monday. It'll just scoot it ahead a little bit. Our exam is going to be Wednesday, and it's going to cover chapters 11, 12, and I will let you know on Monday how much of chapter 13. Depends on how speedy we are today and Monday. I will definitely let you know where the exam line is. And there is mastering due tonight. About half of you guys have already done it because it's stuff we've already covered. So that should be pretty straightforward. And then there's going to be mastering due Monday nights also. Yes, ma'am.
Is it a regular quiz or
Group quiz. Questions on any of that? Okay, awesome. And now I've got our video up and running. Don't forget, you can always go back on YouTube and rewatch all of these lectures. If you get to the point that you're studying, you're like, I have no idea how she does those problems, go back to YouTube, watch them again. Or come by my office. That'd be good too. All right. So where we left off forever ago, we were looking at, not that. We started looking at integrated rate laws. Right, so we're trying to figure out, let me go back a slide. Right, we want to know how long a reaction is going to proceed to reach a concentration that we're interested in. And we want to know, if we know how long the reaction's gone, how much starting material is in there, and how much product is in there. So we talked about integrated rate laws as our way to solve those problems. And we did the first order integrated rate law, which means we're now ready for the second order integrated rate law. All right. So how do I know that this rate equation is a second order reaction? What in the rate law tells me it's second order? Right, this right here, right? That tells me second order. Can I determine that based, if this was my equation, my reaction equation, how do I know that this is not the rate equation for that? I guess it could be. There's two reactants, right? How many reactants do I have in this? One. So that can't be it unless, what would be the one way would be true? If B was 0, right? This could be second order A and 0 order B, right? Because I raised something to the power of 0. It's equal to 1. Does this 2 automatically tell me it's second order? No. What do I have to know in order to figure out second order? What do I have to do? I got to do some experiments. So either I will give you some experimental data or enough information that I'll flat out tell you. The following reaction is second order. That should be the dead giveaway. All right, so let's talk about the integrated rate equation for second order reactions. Right here, look at that. Those are the integrated rate equations for second order. How are those different than the first order? Right, what did the first order have in it? Right, the natural logs. Here, instead, I'm looking at 1/overs. So these are equivalent equations. I can either write this way or that way. They're equivalent. What if I wanted to do my favorite thing in the world? Well, if I wanted to graph it. Which equation is the better choice to graph from? The first or second? Top one. Okay, so if I graph from the top one, okay, true, it would be a positive slope. What would I put on my x-axis? Okay. Oh, that's way too many M's. Time. All right, what would I put on the y-axis? Okay. All right, so then we have a positive slope. And what is the value of the slope based on my equation? Okay. Then the last thing is down here, my y-intercept is 1 over a sub 0, right? What does the sub 0 mean? Initial concentration. So this is my initial concentration, and the slope is positive, which means that as time with too many M's increases, my 1 over concentration also increases, which makes sense, right? Because initial concentration should be bigger than any other point in the equation. So as the denominator gets smaller, the fraction gets bigger. Yes, true. Like 3 people are nodding. Excellent. All right, so I'm assuming 3 people are the 3 people who get what I'm saying. All right, so then let's put it into practice. Let's go ahead and do a practice problem, a very wordy practice problem. So you don't need the first sentence if you're writing it down yourself. You really just need this equation and the rate equation and K. All right, so we have ammonium cyanate in water can rearrange to give urea. I have already determined the rate equation for this process, and I already know the rate constant for this equation. Is this equation a first, second, or zero order? Second. What in the rate equation tells me it's second? Square. Plus, we just talked about the fact that these are going to be second order reactions. And I'm not that tricky. So, right, this is definitely a second order reaction. I'm so excited to be talking to adults after 4 days of staying at home with my toddler. Speaking in whole sentences and having some sort of interaction. I'm back again. Very, very good. And a lot less tantrums in here, which is also good. Unless you guys want to throw a tantrum later, I'll just give you your favorite stuffed animal and lay you in the crib and let you work it out until you're better. All right, so now if I know the original concentration is 0.229 molarity, I want to know how long will it take for the concentration to decrease. So what piece of information am I looking for? I have K. I'm looking for T, right? I want to know how long, which means I'm looking for time. So the trick to most of these equations are going to be reading the word problem and figuring out what piece of information are they asking me for. Are they asking me for the rate constant? Are they asking me for concentration? Or are they asking me for time? Okay, in this case, I am looking for time. So we have our second order rate equation. Use a piece of paper I haven't already used yet. There we go. So our second order rate equation, which we just had, is 1 over A. Right, 1 over A equals KT plus 1 over A0. So from this problem, what is the A that will plug into the Y part of the equation? Is it this number or that number? This one, right? And they gave us K. We're looking for T. 1 over the other concentration. Everybody plug in those. So far, so good? All right, take a second, find your calculator. Just go ahead and work this out. If you don't have your calculator out, go ahead and get it out because we're going to use it a bunch more times today. All right, so 1 over 0.180. So far there, everybody has the same answer? What are the units of my time going to end up being? Minutes. In this case, it may have been better to carry out a few more significant figures throughout the whole thing and then round at the end, because otherwise you end up with 104 dot, meaning that's the third official sig fig. Depending on how you chose to round, that'd be fine. Good there, feeling confident? A little algebra to warm us up? Yes, sir.
Is master chemistry, we had second exam minutes, different problems, so whatever it gives us.
Yes.
Keep it with that.
Yeah, that's the tricky thing about K. K can have any choice of units. And so depending on either what they measured time in, and in this case it happens to be second order, so it happens to cancel all out, but sometimes K has crazy, crazy units. So these ones are going to have to work out by hand probably just to keep track of who has which units. So. Good there, feeling confident? A little warm up, good? Yeah. Well, let's take a look at, if you're taking notes by hand, don't let this page freak you out. Don't freak out. All right, so I went to the lab and I collected some experimental data. All right, that's what it looks like. Let's see if I can coax that more. All right, that's a little better. All right, so I already did number 1. I plotted the natural log of sucrose versus time, and I also plotted 1 over sucrose versus time. When I plot natural log, what order reaction am I plotting? First. That's why I labeled it first. Okay, if I'm doing the 1 over graph, right, that's the second order graph. I'm trying to figure out which of these plots is the better fit. So what piece of information on the graph tells me goodness of fit? Thinking all the way back to last semester. What piece of information? All over here. R squared, right? When you did that spreadsheet lab forever ago. R squared tells you how good the fit is of the line. And what's the perfect R squared? 1. So we want the graph that has an R squared closer to 1. And you can't really read that for whatever reason. This is 0.9998 and this is 0.9847. So which graph is the better fit of your experimental data? Okay, that is the better fit. So if that is the better fit, done, right there. All right, so if that's the better fit, what is K for this reaction? How would I find it? It is the slope. Where would I find the slope on that graph? The equation of the line. So here is K. So then if I know K, I want to find the concentration of sucrose after 175 minutes. So how would I go about figuring out 175 minutes how much sucrose is left there? I would plug it into the equation of the line. That would be an excellent way to do it. All right, so here's my equation, if you can see it. Okay, so that's my equational line, and I want to know after 175 minutes how much sucrose is left. Where do I plug in that 175 minutes? X, okay? All right, let's go ahead and calculate out what y equals then. Somewhere around there, depending on how many digits you decide to take it out to. Everybody get at least that far? We'll do that. Am I done? What is the y graphed in? Right? The y values are natural log of sucrose, which means that this so how do I get the sucrose concentration by itself? Mm-hmm. I don't use this calculator. Oh, there it is. Oh, okay. And what would the units most likely be of concentration? Okay. Good there. Good there. That's as tricky as I could possibly make those problems. Giving you the graphical data, you'd be able to pick out the graph, and then knowing the graph, pull some information out of it. Feeling good?
You have, I guess, plugged in, instead of using that y-intercept you gave us, why couldn't you have done natural log of A?
You could use it. Yep, you could have absolutely used that.
Okay, and then you just pick a point like on there and plug that into the.
Yep, that would all work.
Okay.
Cool. Yep. So you could use the experimental data, knowing A0 was that concentration at time 0. You could use the integrated rate law.
Okay.
And that would have been fine. In fact, that's what I did in my notes. That's how I chose to do it. I knew time. You can't really see it. I knew time, the time, and I knew the initial concentration. So both would have gotten you about the same value. So more than one to skin a cat, isn't that the phrase? All right. So not to leave out our friend, the zero order reaction. He also has an integrated rate equation. If I wanted to rewrite my rate law for this, what's the more appropriate way to write the rate equation for a zero? Just k, right? Because something raised to the power of 0 is equal to 1. So if you have rate equals k, then definitely you have a zero order reaction. So it has an integrated rate equation as well. So let's go ahead and do my favorite thing. We'll draw a graph. All right, so if I graph this, actually, let me rewrite it, the integrated rate law. All right, like that, because it's a little easier to see. All right, so if that's my integrated rate law, what am I putting on my x-axis? Time. What do I put on every x-axis for an integrated rate law? True. Time is always, so time doesn't tell you anything. The x-axis is not particularly helpful in figuring out which order reaction it is. In this case, what am I putting on the y-axis? Yeah, just regular old concentration. All right, which way should the slope be headed? not beheaded. Beheading. Beheading. That's still not good. No. Should be, what's direct? Yeah, negative, right? Going this way. All right, and then this is initial, our B intercept, my intercept. And that's such a boring equation, I don't really have a practice problem for it. I mean, all right, there's nothing tricky, there's no fractions, there's no natural log. All right, this is out of your textbook. This should, if you're thinking I'll never get these straight, is a very handy table. Table 15.1. It's obviously chapter 13 in your book. So they've moved it. Chapter 13 is a very handy little table that says, here's the order, here's the rate equation, the integrated rate law, what the plot would look like, what the slope is, and what the units of k should be for the integrated rate equation. So hopefully that'll kind of help solidify all those different options. Okay. Good, 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 good. Questions on any of that stuff? All right. Let's talk about half-lives. So, everything that we've done so far, right, we knew the initial concentration. We could either find out, or we're given the second concentration, and then we're looking for time, or we're given time, we figure out the second concentration. A half-life is a specific point on our graph. It is the time required for half of A0 to be consumed. So we're looking at how long will it take a reaction to go from A0 to 1/2 A0. All right, I want to know how long that is. We can, if I had a picture, which I do, of what that looks like. All right, here's my graph. Is this it's not an integrated rate law equation because it's not a straight line. It's just a regular plot of concentration versus time. So what was the initial concentration of my reactant? Right, 0.02. So I want to know how long does it take to get to 0.01. Right, you'd find that pot. Looks like maybe 600 seconds. Well, I want to know how long does it take, 660. How long does it take to get to half of that? Right, and then how long to get to half of that? Right, so this would be half, it's a fourth, an eighth of my original concentration. So that's the kind of information we want to know when we do a half-life problem. So again, right, we have all right, that's true for a first order reaction. All right, that's also true for a first order reaction. This is our new equation for first order reaction. If you'd like to show, I would love to show you how to get from here to here. Come by my office. We can do some derivations. We can plug some stuff in. Figure it out. Turns out the natural log of 1/2 is 0.693, which is how we get there. We do some things. Come by. We can work through it. No one ever took me up on the derivations the other day, so someone wants to come by and do some integrations. We can do the same thing. Someday somebody will come by and be like, you know what? I would love to see you integrate that. Hasn't happened yet. Maybe this week. All right, so what do we always do? Let's do a practice problem. All right, so here's my rate equation. That is not a complete sentence, is it? It should be. There we go. So the rate equation for the decomposition of N2O5 producing nitrogen dioxide and oxygen gas is this, right? So what order reaction is this? First, because we just did a first order practice problem, so this is still first order. All right, we know the value of K. We want to do two things. We want to calculate the half-life, and then figure out how long will it take to get down to 1/10 of its original concentration. So we'll do the half-life part first. These half-life problems should be pretty straightforward, right? That's just division. One of these days, I'll remember all the buttons on my calculator. Oh, there it is. How many significant figures can I have in my answer? 2. And then what will the units of time be? Seconds. And again, just about all the problems in this chapter aren't tricky. It's going to be keeping track of the units and those pesky negative signs. They get away from you, so you have to make sure that you know where your negatives are. All right, so the second part of the question is, how long does it take to get to 1/10 of its original concentration? If you're writing out your notes, leave yourself some space. How to solve this takes a few lines of paper. All right. We'll do some thought experiments first, all right? So at T 1/2, right, our half-life, the concentration has dropped by half, right? Right, that'd be true. If I want to do at T 1/4, I would say it's 1/4 of the original concentration. So if I want to know at time 1/10, what should the fraction be? Okay. All right, so I'm looking for the 1/10 original concentration. So I can't use my half-life equation, right, because that's using that. So I have to write a new equation that uses my new concentration. So now I know K, I know the original concentration, and now I know this is the new concentration. So what equation do I need to use to plug in all those pieces of information? We're going to use our integrated rate law. All right, so our integrated rate law is this. Right, in generic terms, that's our integrated rate law. Let's try again. All right, so just plugging in the pieces of information that I know. So if that was my original concentration, that's my 1/10 concentration. I know K, I'm looking for T. What is the first thing you do when you have a problem like this? Not everybody at once. What you're thinking out loud should be combine the variables. right? Get all the things that are similar on one side of the equation and all the things that are not similar on the other side. So what is the one thing that the left and right have in common? All right, that guy. What is the rule if I'm going to do a division of natural logs, or subtraction of natural logs? I gave it away. A subtraction of natural logs is the same as a division. So using our snazzy natural log rules, which if you're not up on your natural log rules, just go back and review them. That move is genius. Why is that genius? I can cancel out some stuff. Bam, gone. So now I just need the natural log of 1/10. And we're like probably a whole minute away from solving it, depending on how fast you are at your calculator. I am pretty slow, so it'll probably take me a little longer than that. How many significant figures do I get in my final answer? 2. And then, what are the units of time? Seconds. So, when you come across these kind of problems, you obviously don't have to work it out this whole way like we just did. You absolutely can. You can keep track of 1/10, 1/10. But it just came down to the natural log of the fraction equals the rate constant times time. Yeah.
Explain again, like how you got the equations for the.
This one? Yep. Right, so that was our original concentration, whatever it was at time 0. And for time 1/2, right, just like we did, it should be 1/2 the original concentration. And if you look at the graph. Right, so at 1/2 the time, it was 1/2 the original concentration. At 1/4, it was 1/2 times 1/2 times 1/4 the original concentration. At 3 half-lives, it'd be 1/8 the original concentration. So I want 1/10 the original concentration. Right, so I want that concentration, 1/10 the original, which is the same as plugging it in right here. That's the concentration I want. Plugged in there. Yeah? Other questions on that? Feeling confident? Using your thermometer? Really good? I'll need to do some homework. Let's do another practice problem. Okay, of the 4 people who are participating, thank you. Sounds like we're going to move on. Good. For those first Fridayers, usually they're a little more chatty than this. Must be all that time off. Slow them down. You hated algebra? Oh my gosh. You must have just had a bad algebra person. Because
No, I had that one classmate that she sat me next to who wouldn't shut up.
that would do it, see? Say it's just a class. In here, fun. Fun all the time. Algebra. We love algebra. We're big fans of graphs.
I didn't realize we had guests.
Sure.
Oh.
You were like talking to like.
They were trying to be funny. I'm like,
Well, yes. Yes, I am. I mean, I'm hilarious.